Hey everybody. So it's been a while since we've been able to get together and do any kind of work at all. And I know that you have been anxiously awaiting the return of math into your lives. So that's going to happen today. If you read my message earlier, we are not covering new material while we are doing NTI days from this point forward. Everything from here on, starting today, is going to be a review. So we're going to go back to the beginning of this course and start a review. You're still going to be responsible for the work, so don't think that just because it's a review and you've already done it once means you don't have to do it again. Several of you missed out on the first part of the course anyway because you weren't doing your work then either. So let's try to turn that around and change things. Before I get started, I do want to just say that I do miss everybody. I'm looking forward to seeing you guys tomorrow during our Zoom class. Please make every effort to join that meeting tomorrow. I will send the link out tomorrow morning on remind to keep you guys aware of when we're going to get started. All you have to do is just click on the link. If you have on your phone, you can download the app Zoom. If you're on your computer, you can just click on the link and it'll open up a web page. So it's not difficult to join. You can choose to join with video or without video. I'd like to see everybody's faces, even if you just pop in for a minute. But I want you guys to get in there just so we can talk. I want you to ask questions, and we'll just go from there. What we're going to start talking about today, like I said, we're going back to the beginning, are the real numbers. And the real numbers are indicated by this. You've seen me write it before, this kind of funky R with two lines through it. The real numbers for our purposes in this class are all the numbers that we know. Had we been able to go on to complex numbers, we would have found, hey, there's a whole new set of numbers that are beyond what we already know. But the real numbers are broken down into two main subsets. The first one is the irrationals. The second one is the rationals. Irrational numbers, if you read the definition here, they are numbers in which the decimal form never terminates and does not repeat. Common examples are pi and non-perfect square roots. The rational numbers are numbers in which the decimal form either terminates or repeats. Rational numbers can always be written as a fraction, where a and b are integers. And then contained within the rational numbers, we have three other sets. We have the integers, the whole numbers, and the natural numbers. The natural numbers are our counting numbers, 1, 2, 3, 4, 5, and so on. The whole numbers are our counting numbers, but it also includes 0. And then our integers are the whole numbers and their opposites. So we have all these positive values greater than 0. We would also include the negative values in the set of integers. So if we were to organize these sets into some kind of a chart like you see here on the left side of the screen, the rectangular field represents the real numbers. So that's everything, all those numbers that we've talked about. Within this rectangular field, we have this circle down here on the bottom left that sits out by itself. That's the irrational numbers. And then we have these embedded circles on the right where we have the rationals. Then we have the integers, the whole numbers, and then finally the natural numbers. And we're going to make distinctions between all these letters over here on the right-hand side of the chart in just a second. So this gives you a visual representation of how these numbers are contained within various sets. So we could look at, if we looked at an irrational number, a rational number, here in set Q, if it's rational, then it's also an integer. If it's rational, it's also a whole number, or it can be a whole number. Sorry, I need to back that up. If it's rational, it's only rational. If it is a natural number, then it's also a whole number, it's an integer, and it's rational, and it's real. So when we get down here into the natural numbers, those numbers are contained within all these other sets. If it's a whole number, then it's also an integer, and it's rational, and it's real. If we are looking at the integers, they are rational and real. And then when we look at the rational numbers, they are rational and real, and that's it. So it kind of breaks things down into like a tree almost, if you want to think about it that way. We have all these numbers that are contained within other sets. Erase that by accident. There we go. All right, so let's look at the irrational numbers. The irrational numbers are represented by the letter I, and we have the number pi, because it's a non-repeating, non-terminating decimal. The square root of 2, square root of 5, square root of 19. There's also the irrational constant e, which is used a lot in exponential growth and decay. Given the predicament that we currently find our entire globe in, e shows up a lot in a lot of the mathematical models that are looking at the spread of the coronavirus. With rational numbers, they are expressed by the letter Q, and those are numbers that can be expressed as fractions or non-repeating decimals, or terminating repeating decimals. So 0.5 is a terminating decimal. 0.33 is a repeating decimal, and 0.33 is also can be expressed as a ratio of 1/3. The integers, represented by the letter Z, are negative numbers, 0, and then positive numbers. No decimals, no fractions. Just going to be whole number values and then their opposites. The whole numbers will include 0, and then it will be all the numbers that we count with, 1, 2, 3, 4, 5, and so on. And then finally we have the natural numbers, and the natural numbers are represented by the letter N, and they start at 1, 2, 3, and so on. So those are the breakdown of those different number sets. Now, when we look at these first 12 examples here, it says to name all the sets to which each value belongs. So we want to find the smallest set that it belongs to first, and then we know that it's contained within all the other sets that are greater than that set. So -10, for example, we know that's not a natural number because those are all positive. Whole numbers are also all positive, but they do contain 0. The next set is the integers. So -10 is contained within the integers, which means it's also a rational number. We don't have to indicate that these are real because these are all real numbers. So we're just looking at all the various subsets that they belong to. Number 2 is a non-perfect square. The square root of 30 is not a perfect square number. So we know that that is irrational, and irrational is its own set contained within the real, so there's nothing else to put there. With number 3, we have 1 7/9. Well, 1 7/9 is also the same as 16/9. This is a ratio. It does not simplify to an integer, a whole number, or a natural number, so it is simply just a rational number. With 24/8, 24/8 does reduce to 3. 3 is a natural number, it's a whole number, it's an integer, and it's a rational number. So that's an example where we get down to the smallest set, and then we contain it's contained within all the sets larger than that set. Number 5, 2.48, that's a terminating decimal, which makes it rational. The square root of -80, or negative square root of 81, is -9. -9 is an integer, which means it's also a rational number because Z is a subset of Q. When we look at number 7, pi minus pi is 0. 0 is a whole number, it's an integer, and it's rational. With number 8, we can rewrite this as the square root of 16 over the square root of 25, which is 4/5. 4/5 is a rational number, and that's it. The only other set greater than the rationals is the reals, and we're not going to indicate that on every one of these. Number 9 is a repeating decimal. So remember, the rational numbers are terminating decimals or repeating decimal values. Irrationals are non-terminating, non-repeating. 109. 109 is a natural number because we can count up to 109. So if it's natural, that means it's also a whole number, it's an integer, and it's rational. Negative 8/3, that is rational only. Negative 8/3 does not reduce to any of the integers, whole numbers, or natural numbers. Radical 7 over radical 7 is equal to 1. We're dividing a number by itself. Even though both of those are irrational numbers, when we simplify it, we do get 1, which is natural. It's a whole number, it's an integer, and it's rational. Some of the properties of real numbers, and you guys have seen these before. So this is all review. So hopefully this comes back to you as you see these things. But the commutative property of addition just simply says that if we have A plus B, it's equal to B plus A. The order of addition does not matter. The same is true for multiplication. A times B is the same as B times A. With the associative property, it's a matter of grouping. How we group these numbers doesn't change the value of the result. So A plus B, if we add those together first and then add C to it, is exactly the same value as if we added B and C first and then added A. And with multiplication, it's exactly the same thing. It's just a matter of grouping. The identity property looks at if we take some value, and in this case we're going to use the value A for addition, what can I add to A to give myself A again? Well, the additive identity is just simply 0. If you add 0 to anything, you get that original value back. With multiplication, it's multiplication by 1. A times 1 is A. Though that is not a big revelation to you guys, A plus 0 is A and A times 1 is A. But we have to understand the identity property in order to compose the inverse properties. So the inverse property of addition just means that we take some number and we add its opposite, which gives us the additive identity 0. Same thing is true with multiplication. We take some value, in this case A, multiply it by its reciprocal, and it gives us 1. Which is the multiplicative inverse. And then finally, the distributive property. You guys have seen this time and time again. We have some number times a quantity. We distribute the A through that quantity, and we get AB plus AC. Here in 13 through 20, we're going to name the properties. With number 13, 528, 528. So the order didn't change. But what did change is where the parentheses are located. We changed the grouping. So this is the associative property of multiplication. With number 14, the 6 gets distributed to give us 6 times 3 and 6 times 7. Since we distributed the 6, that means we've done the distributive property. With number 15, we've taken 7y, we've added its opposite to get 0. So that is the additive inverse. With 16, 3a plus 2b is 2b plus 3a. So we've changed the order. That's the commutative property of addition. When you guys are doing your assignment later on, don't just simply leave it as commutative property. Indicate whether it's addition or multiplication. Same for additive inverse, multiplicative inverse, associative property of multiplication. You get the idea. With number 17, x squared 8x1, x squared 8x1. So the order didn't change. What did change is where my parentheses are located. So this is the associative property of addition. With 18, we've multiplied some number by its reciprocal to get 1. So anytime we do that, whenever our result is 1, we have the inverse property of multiplication. Not the whole word. There we go. And then with 19, it's not written in the order we would expect, but in this case we've gone from the left side to the right side. We've distributed the 3, so this is the distributive property. And then finally with 20, we've added 0. If you look back up at our notes, if you add 0, you have the additive identity. So this is the identity property of addition. And we've named all those properties. For 21 through 24, it's asking us to indicate the additive and multiplicative identities of each one of these numbers. Well, with the additive identity, you just add the opposite number to get 0. So what do I add -8 to get 0? It's +8. What do I add to 6w to get 0? It's -6w. 2/3 is -2/3. And the radical 10 is -radical 10. So you just change the sign and you've got the additive identity. With the multiplicative identity, it's the reciprocal. So if it's a fraction, you flip it. If it's not expressed as a fraction, you just simply write it as 1 over whatever your number was. So -8 is not a fraction necessarily, but we can write the multiplicative inverse as -1 over 8. For 23, it's 1 over 6w. For 22, this is a fraction, so we just flip it, 3 over 2. And then the multiplicative inverse for radical 10 is 1 over radical 10. And then finally we get down to our last property of real numbers, and that's what we call the closure property. The closure property looks at whether or not we take numbers from a given set and perform some mathematical operation. Does that generate a number that is in the same set? So hopefully when we go through these 4 examples, what I just said will make a lot more sense. 25 says that the integers are closed under multiplication. So can we take any 2 integers, multiply them together, and generate a new integer every single time? I cannot think off the top of my head of any 2 integers that we multiply that do not generate a new integer, such as, let's say, -6 times 12 is -72. -6, 12, and -72 are all 3 integers. So an integer times an integer does give you a new integer. This is true. Irrational numbers are closed under subtraction. So if I take the irrational number pi and subtract itself from that, I get 0. Well, pi is irrational. Pi is irrational. But 0 is a whole number. So this means that this is not closed under the under subtraction. So the irrationals are not closed under subtraction. Whole numbers are closed under division. That's also false. A quick, easy counterexample is 1 over 2. 1 is a whole number, 2 is a whole number, but when I divide those, I get 0.5, which is not a whole number. So that is not closed under division. 28, odd numbers are closed under addition. This is also false. 3 is odd, plus 5, which is also odd, equals 8, which is even. So it is not closed under addition. If you can't come up with a quick counterexample, chances are it is probably going to be true when you guys encounter this on your assignment. But think about it before you just write down some random answer. Your assignment is only going to be 1 page, front page only, no back page. It will be posted along with this video and these notes. If you guys have questions as you go, please make sure to ask me. Don't forget about our Zoom class tomorrow, and I look forward to talking to you guys. See you soon.